Our world literally runs on electrical machines. I mean, from the massive generators lighting up whole cities down to the tiny little motors that make your phone vibrate. But have you ever really stopped to think about how they're made? How does an engineer start with just a blank page and end up with a powerful humming motor? Okay, let's get into it.
At the very heart of every single design is this fundamental problem. It's a battle for space. It's this constant tug of war. You've got iron for the magnetic path, copper for the electrical path, insulation to keep them from touching, and coolant to stop the whole thing from melting down. Every choice is a compromise, a balancing act between power, size, and of course, cost.
So to really understand how engineers solve this puzzle, we have to start with the most basic part of any electrical machine, the magnetic circuit. You can think of it as the invisible engine that makes the whole thing go, and how you design it pretty much dictates everything else that follows.
Now here's the cool part. If you understand a basic electrical circuit, like a battery and a light bulb, you already understand a magnetic one. Seriously. In an electrical circuit, voltage, or EMF, pushes a current through a wire against resistance. Well, in a magnetic circuit, a force called MMF pushes magnetic flux through a material against an opposition called reluctance. See? It's the exact same principle, just with a different vocabulary.
So what is this driving force, this MMF? Well, you can just think of it as the oomph of the magnetic circuit. It's where you convert electrical energy into a magnetic push. You just take a coil of wire, you pass some current through it, and the more turns of wire you have, or the more current you pump through it, bam, the stronger your magnetic force gets.
And just like resistance tries to stop electrical current, reluctance tries to stop magnetic flux. It all depends on how long the path is and the material's permeability, which is really just a fancy way of saying how magnetically friendly it is. So job number one for an engineer is to design a path, a circuit, with the lowest possible reluctance. And this is a fantastic illustration of what those paths actually look like. See in each of these diagrams how the design carefully guides the magnetic flux? That dotted flux path is like a superhighway for the magnetic energy, always looping through the iron and trying to spend as little time as possible crossing that high-reluctance air gap.
Okay, so you've designed the invisible magnetic blueprint. Now, what do you actually build it out of? This is where the theory gets real fast. Choosing the right materials is absolutely the next critical step. For the windings, the electrical part, it's usually a showdown between copper and aluminum. Copper is an amazing conductor, but man, it's heavy and it can be expensive. Aluminum, on the other hand, is way lighter and cheaper, but it's not as conductive. That means you need more of it to do the same job. There's no single right answer here. It's a classic trade-off between cost, size, and weight.
Now for the magnetic core, that iron heart of the machine, the wish list is pretty clear. You want a material that's super easy to magnetize, that's high permeability, and one that can hold a ton of flux before it basically gets full or saturates. And this is why silicon steel is the hero of our story. It's engineered to do exactly this, making it the workhorse for most machines. But maybe the most important material of all is the one that, well, it doesn't conduct anything. It's the insulation. It's the unsung hero that keeps everything from shorting out. And every class of insulation has a hard temperature limit. And that limit, that often defines the absolute maximum power you can ever hope to get from your machine.
And here is why that temperature limit is so incredibly important. This quote should give you a bit of a chill. Just a 10-degree rise over the limit, and you can slice the machine's life in half. It's not a suggestion, it's a countdown timer. Heat is the ultimate enemy in machine design.
This brings us right to the core challenge of the whole process. It's a constant, high-stakes balancing act. You're always pushing materials and physics right to their absolute limits, but trying not to go over the edge. Every single decision has a pro and a con.
Okay, let's take the wires. You might think, hey, I can save some money on copper by using thinner wires. That means you're pushing more current through a smaller space, a higher current density. The pro is obvious, you save cash, but the con is immediate. Thinner wires get way, way hotter. You're losing more energy as heat, and you're creeping closer to that scary insulation limit.
And it's the exact same story with the magnetic core. You can try to push more magnetic flux through a smaller chunk of iron. Again, the goal is to save on material cost. But if you push too hard, the iron saturates. It's like a sponge that's totally soaked with water, it just can't absorb any more. At that point, your machine's efficiency just falls off a cliff.
So with all these complicated, competing factors, materials, temperature, cost, physics, how in the world does an engineer actually put it all together? How do they find that one perfect, elegant solution that's hiding in all this complexity?
I mean, this is the million-dollar question, right? You've made all your compromises, you've picked your materials, and you've set your limits. How can you possibly know what the final power output is going to be without building a really expensive and time-consuming prototype? Well, the answer lies in one master equation.
And here it is, the output equation. Now, this isn't just some random formula to memorize. This is the blueprint. This is the magic that connects a machine's physical size and its speed directly to how much power, Q, it can produce. It's the tool that turns all those design choices into a real, predictable number.
So, let's just break it down. Fundamentally, a machine's power is tied to two things that make a lot of sense. How big it is, its volume basically, and how fast it spins. Bigger and faster equals more powerful. Simple enough, but there's one more piece to this puzzle. That's C0.
And this is the real genius of it. That constant, C0, is where all that hard work, all of that balancing of trade-offs we've been talking about, gets captured. It's a single number that represents the quality of your design. How much current did you decide to cram into your wires? How close to the magnetic limit are you running your iron? It all gets baked right into this one special coefficient.
So, when you look at these diagrams again, you're not just looking at parts anymore, are you? You're seeing a story of compromise and optimization. You're seeing an engineer who carefully balanced iron and copper and heat to create something that actually works, all guided by that one elegant output equation.
So I'll leave you with this. The next time you hear the whir of a fan or the quiet hum of a transformer, just listen for a second. That sound is the result of hundreds of tiny decisions. Was the designer trying to save money, maximize efficiency, or make it as small as humanly possible? The answer is engineered right into the heart of that machine.